Box Cox transformation for multiple linear regression models and how to apply it in R. We will discuss how to use Box Cox and why it is neat to use. Among certain aspects we will cover, we are going to learn how to fit a multiple linear regression model, how to create graphs to test model assumptions, as well as how to apply the Box Cox function. And you will learn how to read and understand linear models output. Let's go next to work with R now. As mentioned before, we're going to learn how to apply Box Cox for different situations. In the first example we're going to cover today, we will discuss different steps to build a right linear model. And as you can see, we're going to discuss what is diagnostic or how to test the assumption for a linear model, as well as to measure the model performance. Let's see, we will discuss why to apply Box Cox, so stay attentive what I'm saying. Let's see, first you have to fit a linear model. In this case, we're going to talk about two important libraries for speeding up our process. In this case, it's tidyverse for data manipulation, as well as Caret for building better machine learning models. You can see, work comes from data. In this case, I'm gonna unload it from here, you see, and you can see it, what we have here around, and you can check. You can see how many columns we have. We have years, salary. So the idea here is to run a linear model trying to predict the salary for a certain individual given the years working. Then here we're going to plot our data set with certain conditions. You can see any text, the color, certain aspects for the lines, and with the title. You can see here. This is the idea. This. Well, because we only have two variables, one is going to be the dependent variable and another response. Check that if I create a line, more or less it's going to be good, right? With certain errors as suspected, right? Let's see if what is the best line that we can find to fit this. Okay, take into consideration this part here. You can see it's important to notice that when you are creating or trying to find the best line, maybe this part doesn't have any problem. However, this one here a little bit. So take into consideration that. Then, now, because we're going to follow the different steps into building a machine learning model, let's create a test in training set. We're going to use, in this case, a function from the Caret library called create data partition that is going to give us 80% as marked there for training and the rest 20% for testing. Then we create the index here, the indices. As you can see here, create the indices, and following this, we take those indices to take the different observation from any text, that is our data set. The same for test. Now we have two different sets, because you mark here, here, and here. Why do we want to do that? Because we want to measure the model performance given the Box Cox transformation and not. We will see that. Now, how to build a model in R? It's very simple. You just use the function lm, and here you tell what is the data. In this case, I'm not going to use the initial dataset in text. No, I'm going to use the training. You can see here. And what is my explanatory variable? Years. And what is my response? My output? Salary. And don't forget the field here to use. And there you go. We just fit a model. Now the summary. It's important here. Now see here how to read linear model output. Now we have here to see if the model is significant. The p-value is smaller than 0.05, then ds, the r square, or the coefficient of determination is telling me 83%. What else? Here. Is the variable significant? Is year significant? Here, and you can see here the column for p-values. Yes, It's telling me that my variable is significant to explain the salary of the person. And these two values here are the coefficient. Then, if I want to recreate salary given years, I'm going to use that. How are we going to do that? Well, you just type what salary is going to be, following the explanation there, minus 681.1, because that's our intercept, as you can see, plus 9,087.3 multiplied the years. And that's my linear model, simple regression model. Given certain years, I can find what is the salary. Okay? But is this model right? That's the question that comes to us. Is this model right? Well, it's important that in statistics we use certain assumptions for building a linear regression model. Which assumptions? Well, we are going to type here. I'm going to tell you. I'm going to read. Something is, we're going to abbreviate it using line. Line stands for linearity. That means that the relationship between variables has to be linear. What else? Independency. Independency of who? Independency of the observations. One observation doesn't have to disturb how you collect the other observation. What else? Normality. Normality of who? Normality of who? Of the residuals. What are the residuals? The residuals, remember, residuals are equal to the real value, the real y, we're going to say it, minus the observed or fitted y. That's what the model is going to tell us. What is, given certain years, what is the salary? Those are the fitted values. Okay, and what else? This is for residuals. What else? Well, now the E is for equality. Equality. Equality of what? Of the residuals. Then, we're going to check if the residuals are near zero. Why? Because we want to reduce the errors of fitted values with the real values. Let's see that with some plots. An easy way in R is just run plot. And you can see here, it's gonna, you can see here in the console, just press enter. We have certain plots. The first one is what we call homoscedasticity or equality of variance. Check here that we have 0 around here, because it's that want to reduce the errors. The residuals are those errors. And then I want all these errors around this horizontal line. But check something important. This other curved line. What is that? Well, it's telling me that there is some pattern, and we don't want that. We want to avoid those patterns. They should be scattered all around without any visual pattern or obvious pattern. But here I can see it. There is some pattern. That's a problem. That means that there is no equality of variance, because the errors here are different than the errors here. And we don't want that. So there's a problem. Homoscedasticity is a problem. So we are violating. There is a violation of the assumption. The other one is going to be normality. All the residuals have to be normal. Remember that. Normality of residuals. To check, well, we can say that those dots all around this line, yeah, maybe it's acceptable. Then here, scale location, there's no any problem. Maybe there are some outliers, as mentioned here, that could affect the performance of our model or the goodness of fit of our model. Now, here, with that cook distance, it's important to notice if we have certain outliers, but there's no big deal, as you can see, because all these cloud of points are in no such different way. So we don't have problem in that aspect, but the equality of variance is a problem. Now let's check. Other way to bring this information, as you can see, you have salary years. Let's check this, and I'm going to create, or I'm going to plot my information, my training, versus what the coefficients are telling me. The coefficients, where are the coefficients of my model? Here in intake. Outline is going to be a line that is going to recreate what those points should be. Let's check. As you can see here, that was sort of line that I created at the beginning when I was explaining you. And you can see here, as mentioned before, there is this tiny tail that could have make us to have problems, because the other ones are just looking fine. You can see here we have 0, but this one maybe are the ones that are causing troubles that to our goodness of fit in our model. Now we have to do something about it. Before doing that, let's calculate the model performance. That's going to be a baseline for comparing if it's important for us to check the assumption of the model. Let's see here, we use the function predict, and this pipeline is due to type variables, remember, and this is our model, and we're going to try to find what are those predictions or the fitted values. But check that those fitted values are now for test, because I already saw what was the model performance in the output. Remember here, just check here, this is the model performance for the training, but now I want to know for my testing. Important, this observation have been used in or building the model. Let's check here, and now I'm gonna compare. Let's check that R squared, as I mentioned before, is already calculate the root mean square error. It's important, those are the errors, right? The smaller the better. And let's check now here. There you go. Now we can compare it. What is telling us this? Well, R squared is similar to R squared test. That means that this model is not overfitted because they are more or less close. Here, the M squared error, look, that have identical values too. So the problem is not about the model performance, it's about the assumptions. So we're going to compare it with our new model. Now let's go and put some hands in the box transformation. Why to use box Cox transformation? Well, we want our new model to use a new variable. Which variable? Well, our transform variable. Which variable we're going to transform? Well, maybe our dependent variable is the one that is causing our problems. And then we're going to try to change it to a normal distribution. Why? Because that's going to improve our homoscedasticity and the normality of our residuals. Let's check here the original data. Check here. This doesn't look normal at all because it should be something like this, bell shape. It's not looking like that. Then when I use the library math and check something here, we have this transformation. Y is going to be our salary in this case. Then we want to find the best lambda that allows us to transform our variable salary into a normal distribution. Okay, if lambda is equal to 0, of course we cannot calculate the denominator there. You can see it. And then we're going to use the natural logarithm. Important. Well, for that we're just going to call the function Box Cox, and we pass our linear model, previous linear model, and we want to see the plot true. And we have from -2 to 2, that's the default. Then let's create it, and there you go. This is the output. The higher the better. So you can see here which value we should use for a lambda. Say it's near 0, 0.001 or something like that, but near 0. We can calculate it, or you can find what is that value just passing or saving that information directly into a variable, like we call it b, and then you extract which one is the highest value. As you can see, we're going to use 0.1. That is telling us that that should be the best lambda to use in Y transformation. And there are some other information when you use Box Cox. Now, that means that we're going to apply this. We should use 0 or 0.01. Well, in this case, we're going to use 0. We're going to use directly, because it's so close, we're going to use logarithm. Then, you can see, instead of using some transformation like this, we're going to use directly log. In R, we call log for logarithm, and we calculate a new linear model. We're going to call it Unitech fit, always with a training data set, and we create this new model. There you go. The coefficients, there you go. Check that something has changed. Why? Because if the years are going to go now to a logarithm of salary, those years have to be multiplied with the smallest number. Remember that in the past it was something around 9,000, but now it's just 0.08. Of course, this has to be like this. The same the intercept. Now let's check our data, the original data, with the model. But check something here that is important in you see. Plug. In the plot, I put log, not the original data directly, because I need to use transformed with the transformed observations in my linear model. Okay? You go here. It's a little better, right? No problem of any tail here. Wow, terrific. You can see that's why it was so necessary. Of course, for you, I let you to use the 0.1. The transformation uses 0.1, and if compare this model, my model using logarithm, with yours using 0.1, and you can let some comments about it. Okay, something important. The original data, remember, the original data is not logarithm. How can I go back, transform it back? Then here you can see this is my original data. You can see here, when I show you, you see what the thing is. If I have to use logarithm, that means that go back, I have to use an exponential. Remember that logarithm of y, of the salary, is equal to my formula, as I'm gonna write it here. As you can see, I'm gonna print summary again, summary of Unitech fit log. You see here, these values here, and you can use the coef as I already did. Well, if I want to find salary, I'm not going to find salary directly, I'm going to find salary, because that's our model, how it was built. It was going to be 10.46 plus 0.08 times years. That means given certain years, I can find what is the salary, but the log of the salary. And because I want to find salary in the original units, I have to say salary. It's going to be the exponential of all here, 10.46 and so on. Okay, and that's what is written right here, Now, instead of using apply, I'm going to use curve, because that way it's going to curve, show my curve that I have here. Check the coefficient is, that one is the intercept, this one is the coefficient for my variable years, okay? And who is x? Well, x is years, but I'm telling it from 0 to 30 around. So you can see here, it's going from 0 to around 30. Okay, and then let's plot it together, and there you go. Can you see? That means that, do we have a linear model, a simple linear regression model? Actually, yes, because we call this linear due to the coefficients, due to the variables. Even if the variables have some exponential there, but remember that I can separate this. I can find that's exponential of this multiplied with this. At the end, I'm going to have some coefficient multiplied with a variable. Then, yes, it's still a linear model. Okay? This is from some property of exponential, of course, what I'm mentioning. And check then that my construction is not a straight line, but a curved line at the end. Now let's check if this allows us to meet our assumptions. Now let's plot. And the one that was causing problems was equal or variance. And here you go. Check that there's no pattern at all. Now all our dots are scattered all around. No pattern, no visual pattern at all. That's good. Normality has changed. Yeah, it looks the same, but that's not our problem. That's that we can say the less of our problems. And scale location, this looks still okay. No noticeable outliers at all. There you go. Now we can see here what is that. This one is for fitted values versus residuals. So you can see, and we can see it even better than before. There you go. You can see no pattern at all. It's just scattered all around. That's good. And normality, the other way is using Cooper norm. Well, there you go. Now let's calculate the root mean square error. That's the difference of the fitted values with the real values, and we calculate what is the mean of those errors. And check that this is the first model I built, and this is the second one. Let's calculate this. Check here how it dropped. But it's some trick here. That here we have logarithm. Okay, if we really want to really compare the huge difference between 20,000 and 0.16, we have to go to the original scale. Okay, that's gonna be better. Now let's see here. Check that I put exponential again. Okay, and here you go. Here we have a 20,000, and here now we can compare the real values in salary for training and the fitted values. Let's check. It's more than 4,000 units. It dropped more than 4,000 units, and that's great because remember, we want to reduce those errors, mean square error or root mean square error. Here you have, and remember what happened with the R squared. The coefficient of determination is still good, more than 88%. Still good. Now let's make some predictions to calculate how it is compared our training with our testing for our new model. Let's check here that I changed it to exponential because the results here are a logarithm of salary. Okay, that's very important. That's very important. Now we can compare. Check this. I put in exponential of the fitted values for that training, and here directly for our test because I just converted. There you go. Now you can see that test dropped a little bit compared to R squared. That's okay, and you can notice here that 87 is due that we had logarithm, and now here are the original data. So you can see for the exponential compared with the training values. You can see, and the errors are still, we'll say, greater for the test than for the train, but it's good. The model has improved a little bit. Noticeable? Yes. And we met the assumptions. Okay, that's how you apply Box Cox and logarithm. It is important how to use Box Cox and how to use logarithm transformation in R for regression models. See you next episode talking about more regression models